So we are on our way to a statement about the energy stored in magnetic fields by inductors, but I want to take this opportunity to get you to go back through your formulas again. So could you please write the equation that defines inductance? Stop the show. When you have done it, you start the show again, and some form of this, maybe with the I divided in this links equation. Now write Faraday's law of induction, not in terms of integral E dot ds, but in terms of this EMF. You've started the show again, and that's when we drag this back in. Oh yeah, of course, we know all of that. Next, I'm going to drag on a formula for the voltage across an inductor. This is Faraday's law of induction, but what about the potential difference between the two sides of an inductor? And you may or may not have recalled that you have this formula that we got there, starting here and taking the derivative of both sides, and then recognizing that the derivative of this with respect to time was equal to the EMF, and so on. Now, next question. What is that equal to? What would its units be? And I'm not even going to put the answer here, but you will put it on your worksheet. What about this? What would its units be? What is that equal to? And then we take those two ideas, and I want to take this RL circuit, and we're going to Kirchhoff around the RL circuit, but and there is always this problem that the results we get might apply to this particular series arrangement, but if there was a different arrangement, we would get different results. That is not going to be the case today. But at any rate, we will take this simplest of RL circuits and Kirchhoff around it. We'll have a voltage gain and a voltage drop and a voltage drop. Boom, boom, boom. And now we're going to do the magic. I'm going to multiply through this equation by current. And I get this, and we recognize, since you got those right, we recognize that this is the power in the seat of EMF, and here is the power in the being dissipated in the resistor, and so it follows that this must be the power being dissipated in the inductor. So I will take that expression and set it equal to the rate of change in the potential energy of the inductor. Then I'll take this equation and multiply both sides by dt. I changed the order. I brought the du over here and the LDI over here. LIDI. Now I will integrate both sides of this, so I'll get potential energy here. But when I integrate this, remember that inductance is not a function of the current. It was dependent solely upon the geometry of the inductor. And so this is the only thing that is a function of current. And when we evaluate that integral, we get this result. And so it follows that the potential energy stored in the magnetic field of an inductor is given by this formula. Do you remember a similar formula for the energy stored in a capacitor? that would be a worthwhile exercise for you. It was stored as electrical energy in a capacitor, and it was Q2 equals 2Q. Oh yeah. Oh yeah, Mr. Houghton, you've been so kind to us with our lovely mnemonics. Yes. And notice the analogous structure here, that the magnetic field is due to current, the electrical field due to charge, and that this factor here, changing sides of the fraction bar. Oh yeah, okay, so new formula. Learn it. Again, an opportunity for review. And yeah, I think we've moved on from what we needed to do, and this is our extra. This is actually chapter 32 material, but this seemed like a good opportunity, and there would not be, it would get too busy later. So here we go. Pull them out. Pull them out of your head. Gauss's law for electricity. I see you have pulled it out and written it on your worksheet. That's why you started the show again. And people, if you deny yourselves these opportunities, you are just going to find yourself sorry that you don't know these things. You need to push yourself to memorize this stuff. Okay, so this was the idea that a source of field can be used, that the source of field contained within the Gaussian surface, would have this relationship to the field at the area, the surface area of the Gaussian surface. So based on that, this idea that if you looked at whether the net field was going in or going out, and it added up to some non-zero quantity that you could know about the source contained, that ought to also work for magnetism. That if there was a source of magnetism contained inside of here, be it a positive or a negative source, then there ought to be a net flow of field either into the Gaussian surface or out of the Gaussian surface. And so we could do a Gaussian integral B dot dA, and that would equal to, probably it would be mu naught don't like this, I messed up. This should be a mu. Drat. Not worth the time. Okay. And it shouldn't be down there. It should come up top. This is on the bottom. This should be up on the top. So this source of magnetism contained in the Gaussian surface would then have this relationship to the magnetic field dotted with little patches of area and add them all up. But the source of magnetic field is like a magnetic north. But whenever you have a magnetic north contained in a Gaussian surface, the magnetic south is going to be right there with it. So far, nobody has found a magnetic monopole, and I don't know why they keep looking. It seems like an impossibility to me, but do I know? But there always you get a magnetic dipole, and so the net source of magnetism contained is always going to be zero, and so it follows that Gauss's law for magnetism, if you take the magnetic field at a Gaussian surface dotted with all the area of that surface, that the source of magnetism contained is always going to be a net zero. So there you have Gauss's law for magnetism, and you'll get a chance to apply that. Next, and we're developing Maxwell's equations here. We're up to the third, and we've already done it. Faraday's law of induction. Let's do it not set equal to EMF, but set equal to E dot ds, the integral E dot ds. And you can fill it in. Yes, you can. And you've done so. Bingo. And usually they leave the capital N off. I guess it's wrapped in here to the flux already if you have multiple loops. And Ampere's law, which you also recall. Yes, you do. You're so good. So here you have the rate of change in magnetic flux results in an electric field. But you don't have the same thing here. But symmetry would suggest, shouldn't the rate of change in electric flux result in a magnetic field? Here you have current giving rise to magnetic field. Well, shouldn't you have something like a magnetic current giving rise to electric field? But of course there is no such thing as a magnetic current because there are no magnetic monopoles. So I understand why we don't have that, but why don't we have the rate of change of electric flux? And that's what Maxwell said as well. And so he modified Ampere's law to not only have Ampere's law part, but this contribution where the rate of change in electric flux gives rise to magnetic field as well. And it's not negative like that one was. And it's got this ugly stuff out here in front. But that's what Maxwell's theory led him to. And so there you have Maxwell's equations in all their glory. And I expect you to understand them. I expect you to memorize them. And I expect you to be able to explain them to other people. And have a smile on your face like, isn't this clear and obvious to everybody? Let's go back to this ugliness here. Please get out your calculators. I recall for you what the permeability constant and the permittivity constant are. Will you please, on your calculator, multiply those two together? And admittedly, it doesn't look like much. Now, will you take the square root of that product? It still doesn't look like much, Mr. Houghton. Now, take the reciprocal of that. Wow, way cool. We'll talk about that some more. Okay, Maxwell's equations. And why is this here? I just want to deal with another idea that Maxwell developed, that here you have a current flowing, and that of course is going to give rise to a magnetic field that encircles the wire. But suppose you had a capacitor, a parallel plate capacitor, then as the current flows, you would get more and more positive charge on this plate and more negative charge on that plate. That is, the electric field would be here, but the electric field would grow. So you have a changing electric field. And if you put a membrane, an area down through there, you could talk about the flux, this field going through that area, and there would be changing flux, this thing here. And it would lead to a magnetic field. Maxwell gave a name to this growing electric field. He called it displacement current. It's not really that charge is moving through that space, not a true current, but instead this growing field, because you have this displacement of charge on the two plates, was I think what he was referring to. And as a result of that, you do get this magnetic field around the current, and you get a magnetic field around the changing field. That this part, the changing current giving rise to magnetism, and Maxwell's contribution, the changing electric flux giving rise to magnetism. All right. And you have a checkpoint, and these are all Gaussian surfaces, and you're asked about magnetic field. So you're going to want to use Gauss's law for magnetism, which I hope you have in your head already. But do this problem. I think it will be valuable to you. Now, this essay, which comes from your book, and it is so outrageously over the top that I thought it bore a public reading. So you can either parse along with me, or you can close your eyes and just revel in the glory of this rhetoric. All equations of physics that serve, as Maxwell's do, to correlate experiments in a vast area and to predict new results have a certain beauty about them that can be appreciated by those who understand them on a purely aesthetic level. This is true for Newton's laws of motion, for the laws of thermodynamics, for the theory of relativity, and for the theories of quantum physics. As for Maxwell's equations, the physicist Ludwig Boltzmann, quoting a line from Goethe, wrote, "Was it God who wrote these lines?" In more recent times, J.R. Pierce, in a book chapter entitled Maxwell's Wonderful Equations, wrote, "To anyone who is motivated by anything beyond the most narrowly practical, it is worthwhile to understand Maxwell's equations simply for the good of his soul." The scope of these equations has been well summarized by the remark that Maxwell's equations account for the fact that your car starts when you turn the ignition key. No, the fact that a compass needle points north, that light bends when it enters water, and your car starts when you turn the ignition key. These equations are the basis for the operations of all such electromagnetic and optical devices as electric motors, telescopes, cyclotrons, eyeglasses, television transmitters and receivers, telephones, electromagnets, radar, and microwave ovens. James Clerk Maxwell, who was born the same year that Faraday discovered the law of induction, died at the age of 48 in 1879, the year that Einstein was born. One is reminded that Newton was born in the year in which Galileo, his illustrious predecessor, died. Maxwell spent much of his short but highly productive life providing a theoretical basis for the experimental discoveries of Faraday. It is fair to say that Einstein was led to his theory of relativity by means of his close scrutiny of Maxwell's equations. Einstein, a great admirer of Maxwell, once wrote of him, "Imagine his feeling when the differential equations he had formulated proved to him that electromagnetic waves spread in the form of polarized waves and with the speed of light."